basically what we're trying to achieve here is differentiation from the first principles, right? So the differentiation from the first principles. So if we have y is equals to x squared, for example. Normally, if you just do it with the normal formula that we have, in this case, if you have y is equals to ax raised to the power n, then our dy over dx is going to be an xn minus 1. So in our case, our y is, assume that there is a 1 multiplying it, then I'll have our x raised to the power 2, which means our dy dx is 1 times 2 times x raised to the power 2 minus 1. So it gives us 2x. 2 minus 1 is already 1, so this is the answer to x. But if you want to go with the method of from the first principles, so we have in this case here y equals x squared. So we have ever so slight change in our y plus change in y is equals to our x plus change in x. So we expand this bracket to give us x plus dx, x plus dx, which gives us x times x plus x times dx, then plus dx times x plus dx squared, which gives us x squared plus 2x times dx plus dx squared. This is our y plus change in y. So, but we want to subtract our y from this y plus change in y to leave us only our dy. So we have y plus dy minus our y, which will give us x with all the values that we got from our x plus dx, the expansion, then minus our upper the value of our x squared, which is y here, y equals x squared. So, of course, this cancels this thing out to give us our dy, and then this cancels this out to give us 2x dx plus change in dx squared. So now, we want to divide everything by dx. So in this case, it's going to be dy divided by dx, which is same as 2x dx divided by dx plus dx squared divided by dx. So this actually gives us, this cancels this out, and this cancels out only one of these to give us 2x plus dx. And our dy dx is 2x plus dx. So we now do our limit. The limit of our function as of dy over dx as the x tends to 0 is equals to dy over dx. Notice that there's a change in where I wrote this delta y and over delta x. So this is now the dy dx, because it's the limit of the value we get if this thing tends to 0. So if it tends to 0, this thing goes out. This changing in our x, delta x goes out to give us 2x. So this is the value of our dy dx using the first principles. So we eventually got the same answer we had when we did it using this formula. But this is a longer, more crafty version of our dy dx. This is to differentiate from the first principles. This is much longer. So for example, if you have something like x3, x4, x5, as the case would be, you can achieve it with these, but it's going to take a very long time. That's why we use this formula or algorithm to be able to get a very quick value. So for example, if y is equals to x raised to the power 5, we have dy over dx using the formula 5 times 1 x raised to the power 5 minus 1 gives us 5x4. Immediately just gotten the answer. Then to take our time to expand the bracket into 5 times. So it's more convenient to use the formula, but this shows you in detail what really happens under the hood. So these are like 2 ways of achieving a differentiation. But what we did here now is the differentiation from the first principles.